Hey astronomy students, for those of you who haven't done this lab yet, I'm going to show you how you can plot the data in Excel, get a nice graph in Excel. You might argue that, well, then you're missing out on the practice of doing a graph by hand, which is valuable, but it's also valuable to know how to do it on a computer. I'm going to speak here as if you've already read through the lab instructions. We've got some data here that we need to plot. We're talking about the speed at which stars move around the centers of their galaxies. And we're given, for various distances from the centers of the galaxy, I'll just talk about this individual galaxy, I forget the name of it, and New General Catalog 2742. So we've got data points for stars all the way out to 10 kiloparsecs from the center of the galaxy. A parsec is 3¼ I believe, light years, and kilo, of course, is 1,000. So 10 kiloparsecs would be something like more than 30,000 light years from the center. That number makes sense because, as I recall, our own galaxy is maybe 100,000 light years across, and we're almost, I think we're almost towards the edge, which would be 50,000 light years, or something like 10 kiloparsecs, 20 kiloparsecs. Okay. So what I'm going to do is take the data off this graph. That's what it is. Here are the various radii from 1 to 10 kiloparsecs, and we read the velocities off the graph by looking at their vertical coordinates. And that requires some interpolation because they've only marked off the velocities in intervals of 20 kilometers per second. A kilometer per second is something like 2/3 of a mile per second. So since a lot of these markers are in between lines, we'll have to guess. Like this one, for instance, is a little higher than the midpoint, so it's going to be a little higher than 150. I'll probably just demo a few of these and then pause and come back. So I'm going to pull up a spreadsheet here. Now this one's already done, but I'll demonstrate how to do this from the beginning. We need to label some column headings. So first I'll start with distance from galaxy center. Stretch out this cell here. And I need numbers going from 0 to 10. So I'll start by entering the 0 manually, and then for the next row I'll say this radius equals the previous radius plus 1. And Excel is smart. If you hover over the lower right corner here and click and drag, it will repeat that calculation for subsequent rows. So that's a quick way of creating a column of numbers from 0 to 10. Also, I should really practice good habits here and include the units. The distance from the galaxy center in kpc, kiloparsecs. It's kind of awkward that the cell is so wide when I only need a very narrow space for the numbers. So what I could do here is I'm going to insert another column, and then I'll highlight or select these cells together and go to merge and center. Did that work? Not quite the way I wanted it to work. Merge cells. What if I unmerge cells? What just happened here? Okay, if I click merge and center, it looks like the type is centered left-right, but I also want to center it vertically because it looks awkward, so I can use this button. There we go. That's what I wanted. And that way, when I contract, that also didn't do what I wanted. I think word wrap is what I want. Wrap text. Much better. Okay, now this cell isn't quite so wide. I need another cell. Let me merge and center these. Hit this button as well, wrap text. And that's for my, now I have an extra cell here. Or an extra row. Let me get rid of that. This one's going to be called, technically it's radial velocity. I'll explain what that means in a minute, but I'm just going to type velocity in kilometers per second. When you're looking at a faraway star, you can really only detect If you're using the Doppler shift method, which we talked about in previous lab, you can only detect the motion that's directly away from you or directly towards you, which is called the radial velocity. So the data for these speeds of the various stars that were looked at is actually incomplete. Many of the stars are actually moving a little bit faster than the numbers given here, because these numbers only show the component of the velocity away from us or towards us. Overall, the star could be moving away and sideways, for instance, which means its overall velocity would be a little bit greater than these numbers. And here's where I just read off the values and put them in the graph. So I'll demonstrate a few and then pause. This very first one, well, the first one would be this one, 0, 0, so enter the 0. And then for stars at a distance of 1 kiloparsec from the center of the galaxy, they look like they're going almost exactly at a speed halfway between 80 and 100, so I'll just enter the number 90. Stars at a distance of 2 kiloparsecs, also basically halfway between 100 and 120, so I will enter 110. So you can see that for stars farther away from the center of this galaxy, those stars are moving faster. They're whipping around faster, which is different from our solar system. The stars that are farther out actually move slower. But the reason for that is the speed at which the stars whip around or orbit the center of the galaxy depends on how much mass lies within their orbit. And a galaxy is a much different structure than a solar system. For the solar system, most of the mass is in the sun. It's concentrated in that ball at the center of the solar system. But a galaxy has stars spread throughout. Let me keep going until we get to one that's a little more difficult to interpolate. These are pretty easy. Number 4. Okay, so you can see this one's, it's not right on top of 140. It's also not as high as 150, which would be the midpoint. So I have to guess. I suppose I could zoom in. No, I can't zoom here. I'm just going to guess that it's like 2/5 of the way from 140 to 150. So I think that would be 144. Right? Maybe it's 143. I'll go with 143. It doesn't have to be perfect. Same with this one. It's higher than the midpoint. It's not just 150. It might be 157 or 158. I'll put 157. So let me pause and complete this column. Okay, next up is to do a calculation on this data. I mentioned a moment ago that the speed at which these stars whip around the center of the galaxy is determined by how much mass lies within their orbit. The more mass there is within the orbit, the faster they'll move around. And we can be more quantitative than that. We actually have a formula. This comes from physics. This is something that we actually use in our physics classes at Long Beach City College. 3A, for instance, Physics 3A is something, or that's a class where we talk about this. In any case, let me merge these cells, center vertically, wrap text, and then the title of this column will be mass, and the formula given to us here will allow us to calculate the mass as a multiple of the sun's mass. So I'm going to put solar units. For instance, if the number came out 100 for the use of the formula, that would mean that all the mass within the orbit of a star is about 100 masses, or excuse me, 100 solar masses. Now, it turns out the numbers we're dealing with are much bigger than that because galaxies have millions or billions of stars in them. So here's where Excel can save you a lot of time. Rather than using a calculator to punch all of these in individually, manually, I don't want to apply the formula for the first data point. If we look at the formula, obviously if we plug in 0 for R and 0 for V, we're going to get 0 for M. So let me just enter the number 0. And it's in the next cell that I will actually calculate using the formula. Now the formula makes reference to this quantity G. Big G is a number from physics that quantifies the strength of gravity between two point masses, meaning two small little particles with mass. They're giving us the value of G, and I want to make repeated reference to that value in my spreadsheet. So down here, where I've got some space that I don't need, I'm going to type the letter big G. And why is my keyboard not working? It's extremely irritating. This is the first time I'm using Camtasia here. Nothing's working. All right, I don't know what that was about, but it seems to have resolved itself. So down here in the empty space, I'm going to make a cell that says G. I think I prefer to have that letter be on the right side. And then here's where I enter the formula. Now, since I'm implementing scientific notation, Excel requires me to put an equal sign, like I'm doing math. 4.31 times, I use the asterisk, 10 raised to the, and then I put the, this is shift 6. The power of 10 is -6. I hit enter. I don't like the fact that Excel has converted that into decimal form. I want to keep it in scientific notation. So I right click, I go up to Format Cells, and I leave it in scientific notation. Cool. Now I can implement this formula here. So in order to calculate the mass within the orbit of a star at a distance of 1 kiloparsec from the center of this galaxy, I use equals. I need the square of the speed. So that's this number here. I'm going to click on the cell containing the speed, which we read off the graph, and I need to square it. So I use shift 6 for exponent, and then the number 2. That's v squared times the radius. I click on the radius, which is in the first column, and then I divide by the value of big G, which is down here. Now for big G, we're making what's called an absolute cell reference. In a moment, I'm going to repeat this calculation all the way down the column, and for each row, Excel is smart. Excel knows that what I want to do is use this speed and this R in the calculation. In the next row, it'll use the next speed and the next R. But every time I want to use the same cell for G. In order to prevent Excel from looking in the lower rows for G, I have to make an absolute cell reference, and one way to do that is to hit F4 on the keyboard. Now on my laptop here, I need to use the function button first. You may not have to use the function button, but if I hold down function and then F4, I pick up these dollar signs. See where the row and column are specified? Column B, row 17, there's a dollar sign in front of each. So now every time Excel does this calculation all the way down the column, it's going to look in this cell for big G instead of down here somewhere. And Excel was nice and gave me the answer in scientific notation. So evidently, the total mass within the orbit of this first star, which is at a distance of 1 kiloparsec from the center of the galaxy, E plus 0.9, that means times 10 to the 9th. That's the power of 10, which is a billion. So 1.8, that's almost 2. There are almost 2 billion solar masses worth of mass within the orbit of the star, which is what we expected because stars, we know, have billions galaxies have billions of stars in them. Some of those stars are more massive than the sun, some are less massive. So here's the cool part. Hover over the lower right corner, click and drag, and Excel will complete that calculation for all the data. See how smart it is to use a spreadsheet instead of doing this manually? So you're welcome to do this for your lab. What's next? I'm going to go back to the one that I already completed to jog my memory here. Luminosity inside R. Right, if you read the lab manual, it's also going to give you some additional data in this column here. I need to get this data into my spreadsheet, and to do that I first need a new column. So as before, let me grab these two cells, merge them, center vertically, wrap text, and then I can type luminosity inside R, and I'll put that in solar units. Once again, I'll enter the number 0 because 0 distance from the galaxy, you don't have any, there's no stars within 0 distance. Of course, there's 0 light coming from there. And here is where I need to enter the number using the equal sign. Anytime you use scientific notation, Excel needs to interpret your input as math, not just text. So I put equals 2 asterisk 10 raised to the, that's shift 6, 8th power. I'm getting this number right from the PDF there. I hit enter, and once again Excel tried to convert it back from scientific notation. I want to keep scientific notation, so let me highlight this whole column of cells. I'm going to right click. I don't think I said that before. Right click, go to Format Cells, and let's see here. I want scientific notation. Great. Now I'm going to pause and finish entering all these numbers. I just read them off the PDF here. What are these numbers telling us? For instance here, at a distance of 5 kiloparsecs from, and that's something like 15,000 light years from the center of the galaxy, within that distance there are about 2.3 billion suns worth of light. Like the amount of light we can measure within that radius of the galaxy appears to be as bright as 2 billion suns. And the next calculation the lab manual asks you to do is to simply take all these numbers and double them to estimate the amount of mass within that distance due to stars. Because something I left out, and you would know this if you read the lab manual, is that all of this mass that we measured previously, the mass that's causing the stars to whip around, it may not actually be from stars and regular matter. It may not be from things that emit light as stars do. And we're about to find that out right now. So let me make a new column, Origin Center, and they're calling it just luminous mass. Luminous mass, and I'll put, this is in solar units. And to do that calculation, it's very simple in Excel. And you could take a hand calculator and just double all these numbers, but I'm going to say this number equals the number in the previous column times 2. And then I hover over the lower right corner, click and drag, and it will repeat that. So the calculations are done for me. Like before, let me right click, go to Format, and ask Excel to display the data in scientific notation. Let me do a quick save here. Now the reason for the doubling is not every star in this galaxy is the same size or mass as the sun. If every star in this galaxy was identical to our star, the sun, then you could count how many stars there were within each distance by just comparing the total light output to the light of the sun, in which case all of these numbers would be the same. But I suppose what we're doing here probably is assuming that many of the stars in this galaxy are not as bright, I suppose, are not as bright as our sun. Maybe there's a lot of stars that are more massive than our sun, but put out about the same amount of light, or maybe there's a bunch of older stars. That's probably it. There's probably a bunch of older stars that contribute a lot of the mass, but just aren't putting out much light. And hence the reason for doubling. And that's obviously a very rough correction there. Okay, here comes one of the main realizations of the lab here is when you look at these numbers, once again, this represents all of the regular, ordinary matter that puts out light. Most matter, well, all matter that we're familiar with here on Earth is made of charged particles like protons and electrons, and we know that it emits light. You know, anything that gets hot, for instance, will glow red, like the coils in your toaster oven. That's ordinary matter. Stars are made of ordinary matter. And when we calculate how much ordinary matter is within various radii of the center of this galaxy, we find that the amount of ordinary matter that gives off light is quite a bit less than the total matter. So this row that I have highlighted, look at this. According to this data, if we go out 4 kiloparsecs from the center of the galaxy, within that orbit there are 3.5 billion stars on average that are as bright as the sun. Let me rephrase that. The amount of ordinary matter, light-emitting matter, that we can see within that distance is about the same as 3.5 billion suns. And yet, there's actually 1.9 times 10 to the 10th. Now, 10 to the 10th, that's like 10 billion. There's almost, I'm going to say 5 times, let's say 5 to 10 times as much matter within that radius as matter that we can actually see. So we see this much, but there's actually this much matter, which suggests there's a bunch of matter within that orbit that we don't see. And that, of course, is what they call dark matter. And I'm no cosmologist, but that's one of the hottest topics in physics right now, in astronomy, is what is the nature of this dark matter? Because it's certainly not made out of protons and electrons. If it was, it would put off light and we would be able to see it. We don't see it. Instead, we detect its existence, we think, because of its influence on the ordinary matter. All we have to do is look at how quickly these stars move around the centers of their galaxies, one galaxy in this instance, and we see that there's got to be a bunch of matter there that's gravitating on these stars that we don't see. All right, what's next here? I think now they're going to ask us to graph, but first they say, what percentage of the total mass is luminous? So we're supposed to look at the furthest point from the center of the galaxy. I go back to my data here. That would be out at 10 kiloparsecs. And it looks like we can see within that radius, and that radius is far enough out, I guess that would encompass the whole galaxy, or close to it. We can see 9 billion suns worth of mass, but there's even more mass there. So I can actually do the calculation right here. I want to compare the mass that we can see to the mass that we know is there because of its gravitational influence. I'll do that calculation over here. I'll say percent luminous and since I'm using math, I have to use an equal sign. I'll say equals the amount we can see compared to or divided by the amount that we know is there. And then to convert that to a percentage, I will multiply by 100. Right? And I don't need this to be in scientific notation, so let me go to Format Cells and just click on Number. And I don't need all those digits, so this is a good button to know. Decrease decimal. I think 2 digits is just fine. So evidently, wow, only 13% or roughly 10% of the matter in the entire galaxy is actually luminous, meaning ordinary matter made of protons and electrons. According to this data, something like 90% of the mass that we think is there because of its gravitational influence is not regular mass. So what the heck is it? Here comes the part where we graph, and this is where Excel is especially useful. We need to graph mass vertically and radius horizontally. So they gave you a piece of graph paper at the bottom. The vertical numbers represent how much mass is within the orbit at various radii, and then these are the radii themselves. We're going to get some sort of curve. Now, before I actually make the graph, I'd like to do some formatting here. Anytime I have a column heading, I like to use a different font. This is something I picked up from a book on spreadsheets. That's probably the nerdiest thing I've ever said. In any case, I like to use a different font. Let's go with Arial. And now I can't, now the words don't fit, so how do I fix that? See this? Oh man, that's going to irritate me. Can I stretch that out? And then it's kind of nice to have borders around the cells, so I'll just put all borders. I'll be adding some more cells here as well. Okay, for graphing, let me do these two real quick. Different font. The type of chart. Excel likes to call a graph a chart. The type of chart we'll be using is a scatter plot with the dots connected. So one way of creating a chart, and if you're using the web-based version of Excel or Google Sheets, it's going to be a little different. That's why I like the desktop version, because I'm used to it, and you should be able to get that for free through the school. Go to Insert, open up the chart menu, and rather than just connecting the dots I want to have the connected curve without the dots. So this is the one that I'll go with. Right now it's blank. You could highlight your columns ahead of time and let Excel guess about what you want to plot, but this gives you more control. Right click in the chart area and go to Select Data. And we need to add a data series. We're actually going to be adding 2 data series because we'll plot 2 sets of data simultaneously on the same graph. So for my series name, the first thing I'll do is plot total mass versus distance from galaxy center. So I'll put total mass versus distance from center, meaning galaxy center. Remember in high school algebra when you plotted things on the vertical axis versus the y-axis, you called it the y-axis. What did I just say? Vertical versus horizontal. You called the horizontal coordinate x, and we typically call the vertical coordinate y. Well, in this case, we're actually plotting, on the vertical axis, we're plotting mass, and on the horizontal axis, we're plotting distance from the center. So these are my so-called x-coordinates, as Excel will refer to them, and the mass data are my y-coordinates. So for the x values, I'm going to click and drag across the numbers for distance from the center. Then I go to this field here. They always put this bracket with the 1, delete all that, and then click and drag across the corresponding masses. And this is important. Excel is a little picky. You have to hit the tab button to get out of there in order for Excel to remember that bit of instruction. And then I can click OK. And for now, I'll leave it as is. And then check it out. We can see that as you move away from the center of the galaxy all the way out to 10 kiloparsecs, the mass within the orbit is increasing the whole time. That makes sense because as you go farther out, there's more and more mass in the form of stars with their planets and all the dust in between. There's more of that within the orbit that you're describing. Now, in a minute, we're going to add units here. In fact, I'll just do that now. If I go to the plus sign, I can add some axis titles. Now I have the opportunity to click here, delete those words, and put, we'll label the quantity that we're talking about, and we'll include the units. So this is distance from galaxy center. And I could use KPC as the abbreviation, but I will type kilo parsecs. Parsecs. Okay, kiloparsecs. And then for my vertical axis, we're talking, of course, about total mass. And those units are solar units, not kilograms, for instance. I'll just put solar units. So if the number at the end here is close to 7 times 10 to the 10th, well, that would be 70 billion solar masses worth of mass. So this is looking pretty good already. The lab manual is also asking you to plot on the same graph just the luminous mass versus distance, because that will allow you to compare the two visually. So to do that, you can right-click in the plot area. Don't right-click on a point itself. And go back to Select Data. Actually, I don't think it matters where you click. We want to add another data series. And I'm going to anticipate here. I need to click and drag across this column, and my window is kind of blocking it. So, add data series. This time, we'll be graphing just luminous mass versus distance from center. Just like before, our horizontal data would be the distance from the center of the galaxy. But this time, the vertical data is from just the luminous mass. That's this last column that we calculated. Okay, don't forget to hit Tab, hit OK. Great. And it will automatically show up as a different color. Now you could change that color if you wanted. I don't know what happened to my, the title of my graph seems to be gone. So let's go back to, hey man, where's the plus sign? I need that plus sign. Oh, there it is, okay. What if I stretch this up? Is the title still there? It doesn't seem to be there. So if I go to plus sign, chart title, I guess by adding a data series, it confused Excel. So I'll put just mass versus distance from galaxy center. And I also want a legend. Remember when I entered the data series, I gave each series a name? Excel will automatically put those names next to the color. So anybody looking at this graph knows which data set is which. Cool. Let me save this. And it's a little inconvenient to have this graph overlaid on my data. So what I can do now is right-click. Let's move the chart, and we'll move it to its own sheet. See, down here, you'll be able to access the different sheets of your spreadsheet. Click New Sheet, and I'll label it Plot of Mass versus Distance from Center. Oh, I'm limited here. So I'll just have to go with that. Click OK. And now I can move back and forth between the data and the graph. Now, I think I'll rename this. So if I right-click here, I can call this data. And I'd like to have the data be the first. All I did was click and drag there. I want that to be on the left. Okay, so we're just about done here. You can see the appearance of the graph changed a little bit. It's like the numbers got shrunken. That's one of the disadvantages of putting it on its own sheet. There's probably a way to tweak that, but I'm still fine with this. When we look at this graph, we can see just how much more unidentified mass there is than luminous mass. The orange graph tells us how much mass there is from stars, planets, dust, stuff that actually emits light. Now, you may not think that dust emits light. It doesn't emit visible light, but believe it or not, your body, for instance, emits light called infrared light. You know, when we turn off the lights at night, we don't see ourselves in the dark, but your body does emit what's called infrared. It's like a color beyond red, and there are some animals that can see that light. And the same thing goes for even cold dust way out in interstellar space. It may not emit visible light because it's not hot enough to do that, like the coil in a toaster oven, but it is emitting radio waves, for instance, maybe infrared if it's warm enough, and astronomers can detect that light. So anything made of regular matter, meaning protons and electrons, will emit light and will also absorb light. And yet there seems to be 90% of the mass in this galaxy that's responsible for the gravitational attraction and hence the orbital motion of the various stars in the galaxy. 90% of that mass is not visible. It doesn't emit light. Very bizarre. That's why they call it dark matter. What's next? That's most of the lab, but they're also going to ask, and you can figure out how to answer these questions on your own. Where does the dark matter tend to be concentrated more? Well, let's take a look at the graph here. We would really have to look at the ratio in each case, like how high is the orange compared to the blue. And I'm thinking that if you go towards the edge of the galaxy, that's where the orange curve is least in comparison to the blue. Right? Like the height of the orange curve here at 4 kiloparsecs from the center looks to be 1/3 to 1/4 of the total matter. But here, it's less than that. Let's see, 1, 2, 3, 4, 5, 6. It's like 1/7 maybe. So I would say it appears as if there's more dark matter at the edges of the galaxy, and I believe that's confirmed in some of the background information here, or in those slides that were posted on campus. Okay, the last thing here is we have to make one more graph, and they're only asking you to compute, additional data for a few rows, but with the spreadsheet we can do it very quickly with all the data. So what they're telling us now is, here's a different formula that we use in physics. This comes from a branch of physics called mechanics. Isaac Newton would have been the first person to figure this out. What we can do is plug in here just the mass from stars, just the luminous mass at the various distances from the center, and figure out if that was the only mass in the galaxy, how fast would the stars be going then? I mentioned, Kepler's third law, right? The planets that are farther out, they move slower through space. It's different from a galaxy. Very often, the farther stars, the ones that are farther out, they actually move faster because as you move out, you're collecting more and more mass within your orbit. But let's go back to the spreadsheet, to the data, and make another column. And I'll put, what did I call it when I already did this? V alternate. Yeah. Oh, you know what? While I'm here, we'll do one more column here. We can merge, center, and I'll put percent luminous. And what I'll do is equals, I want to take the amount of mass within the orbit that's luminous and compare it to, divide by the total mass, multiply by 100 to turn that into a percentage, and then click and drag to repeat that calculation. Now here I'm dividing by 0, which is a problem, so let me just delete that and enter the number 0 manually. It's actually irrelevant because there's no mass of any kind at 0 distance. And this is way too many digits, so let me decrease the number of decimal points. We'll just round to the nearest integer. That's fine. So this helps us answer the question that we were just discussing. You can see out at the edge, the luminous matter does in fact make the smallest percentage of the total matter. Towards the center of the galaxy, a good 20% is from things we can see, stars. Towards the edge, only 13%. Right? And these numbers are all approximate. So, lastly, my last column here, let me merge and center, and I'll call this velocity alternate in kilometers per second. This is the velocities that we might expect to see if the only mass present was the luminous mass. And that's where I have to use this formula. So I'll just manually enter the 0 at the beginning. And then here I'll say the velocity we would expect equals, to use the square root function, just type squirt, S-Q-R-T, open parentheses, and I need g times m divided by r. So let me click on the cell for g. You'll recall we have to make an absolute cell reference, so tap F4, in my case it's function F4, times, that's the asterisk, times the luminous mass in that row, which we already calculated, and then divide by the radius, which is this number over here, close the parentheses, and if I did this correctly, Excel should use this formula to calculate the speed. Let me double click. Wait, you could double click or you could just click and drag. I'll click and drag. And there are my theoretical velocities if the only mass present was luminous mass. But I'm going to get rid of all these decimal points. That's obnoxious. That will be just fine. And check it out. Look how these numbers compare to the actual velocity. See how much faster the stars are actually hauling ass around the center of the galaxy compared to what we would expect them to do if the only mass present was the mass that we can actually see. They're moving much faster than they would be if there were no dark matter. So lastly, let me put some borders around here, change the font. You can also change these to bold type. I like to do that as well. But now they got even bigger and they don't fit. So Control Z. Control Z! I wish that worked in real life, right? Just hit a Control Z, undo bad decisions. Okay, and then you can also put a thick border around the whole thing. This is just aesthetic stuff. Are we done here? Yeah. What's the last thing they're asking us? We're going to make one more graph. This time let's graph our hypothetical velocities versus distance from the center. Hypothetical meaning what would the velocities be if there were no dark matter. So I go back here. I'm going to make one more chart, and I'll put this on its own sheet. So once again, insert chart. We'll do this connected chart with no dots, and it'll kind of smooth it out. Right click. And again, I'm going to anticipate that it's blocking the column that I want to highlight, so let me move it off to the side. Right click, select data, same thing with this. Add a data series. I'll put theoretical velocity versus distance from center. And for my x values, like before, grab all of our radii in kiloparsecs, click on here, delete that garbage, and then for my vertical coordinate, it would be the alternate velocities. This is in kilometers per second. Right, that's like basically miles per second times 2/3, I think. Hit OK, or 3/2. OK here as well. And since we've only got one data series, it kept my title. Let me go ahead and add some axis titles. This will be just like before, distance from galaxy center in, this time I'll put KPC for kiloparsecs, and this will be velocity in kilometers per second. These are useful skills to have for other classes where you may have to prepare a plot. You know, Excel isn't really made for scientific applications. I think it gets used more often in business, but you can still use a lot of these useful basic features for science classes. I do it all the time for our physics classes here at Long Beach City College. I'll hit save. I think the last question they're asking us is, how do the graphs differ? If we compare this to figure 1, see this is the graph of actual velocities versus distance from the center, and you can see the velocities max out around 170 kilometers per second. But for our alternate graph, and let me stick this on its own sheet, so, oops, gotta click in some white space here. Move chart, put it on its own sheet, and I'll call it plot of, I'll put alternate velocity versus distance. And that didn't quite fit, so velocity v distance. And I'll scoot this to the end. Come on. Alright, I give up. I wanted to scoot that to the other side. But now we've got our data, and there are two plots. It's really irritating me that I can't get this to the other side. Moving on. I'm not going to have a temper tantrum here. I'm not going to punch my computer because I'm in control of my behavior. The other thing we can see about the difference between these graphs is, do you notice how for our theoretical velocities, it peaks somewhere in the middle and then starts to decline. So the stars towards the edge of the galaxy are actually moving a little bit slower. And that reminds us of our solar system, where Pluto and Neptune, for instance, move quite a bit slower than, way slower than Mercury, which is whipping around real fast around the sun. And the reason is, as you go away from the sun, you're not really gathering more mass within the orbit, because all the mass is concentrated in the sun. But in these in galaxies, you've got mass distributed throughout the disk of the galaxy. So if the only thing present in the galaxy was stars, you would expect, as you reach the edge of the galaxy and continue to move outwards, you're no longer accumulating more mass within the orbit, and so the velocities should start to drop off just like they do for our solar system. But what we actually see in the lab handout for the real data is that the velocity is continuing to increase. Not at the same rate. You see it's starting to level off compared to what it was initially, but we're still increasing all the way out to the edge of the galaxy, which suggests that there's a bunch of matter at the edge and maybe even beyond that we don't see. That's the dark matter. So some of the background info in those slides talked about how they think a lot of the dark matter is in the halo and even beyond. The halo being that spherical region. People used to think that the galaxy was just that disk and then maybe the bulge at the center, but at some point in the 20th century, astronomers discovered that there's a whole bunch of mass above and below the disk in this spherical region called the halo. I think that's all I need to tell you. So hopefully you've acquired some basic facility with the graphing capabilities for Excel and how to do some simple calculations in Excel. But basically, to use Microsoft Excel, as a calculator. It's like a mega calculator because you can do things very rapidly. This is just scratching the surface of all the stuff you can do with Excel. The last thing I'd like to say is if you choose to use Excel to complete the lab, you're welcome to just submit this spreadsheet as an XLSX file. Please make sure it's in that format, .xlsx, so that I have no trouble opening it. And I'll confirm that you've got your plots within the spreadsheet and look at your data. As far as the questions that are asked here, you can write those in, print out those pages, write them in pen, or some of you are tech savvy and you can type over the PDF and then just upload the PDF as well. Okay, so I'll be looking for your attached spreadsheet and the PDF here, and obviously if you do the graph in Excel, you don't have to do the graph here and here. So Excel for graphs, PDF for the answers to the questions. That's it.